Bismillahirrahmanirrahim. Assalamu alaikum. Welcome back to EE340. In the previous lecture, we talked about waves and we studied the parameters of waves. So the first one that we studied is the angular frequency omega. The unit for that one is radian per second. The second one is the cyclic frequency, which is the unit for that is hertz, or 1 over seconds. So these two parameters are related by the following formula. Omega equals to 2 pi times f. The third parameter that we studied was beta, which called the phase constant. The unit for that is radian per meter. The last parameter that we studied is the phase velocity, Vp, and since it's the velocity, so the unit should be meter per second. So in general, we have the following form. A naught is the magnitude of the wave, cosine omega t minus beta z. So now let's take a couple of examples. Let's start with the following one. We have an EM wave propagating in a certain medium. So that medium doesn't have to be free space. So the epsilon for that medium is something like this. Epsilon relative times epsilon naught, where epsilon relative doesn't have to be 1. Actually, we see in this example that this one, the epsilon relative for that medium is not 1. So the electric field in that medium is given by this expression, 25 sine 2 pi times 10 to the power 6t minus 6x. And it's in the AZ. It's a vector in the AZ direction. So the very first step is to determine the direction of propagation. So you can see clearly here that since this sign is negative, it's going to be towards a positive direction. And since it's a function of x, then it's going to be toward the positive x direction. The second one is asking us to find, to compute t, u. Your textbook is using u for phase velocity. In the previous lecture, I used Vb. We're going to use both. And the wavelength lambda. So let's start by computing t. We can see from this expression that the angular frequency is 2 pi times 10 to the power 6 radian per second, and the cyclic frequency is 10 to the power 6 hertz. Therefore, from the previous class, we saw that the period is related to the cyclic frequency using this formula. Therefore, t will be 1 microseconds. The second one is actually the phase velocity or the wavelength. Let's start with the wavelength first. So the wavelength is given by 2 pi divided by beta. We know beta here. Beta is 6. Then 2 pi divided by 6 is 1.47 meter. Then finally, let's find the wave velocity, or the phase velocity here, as omega, the angular frequency divided by the phase constant beta. So if we complete this division, we'll get divided by 6, which is 1.47 times 10 to the power 6 meters per second. We see here that the propagation medium is not free space. Otherwise, this one has to be if epsilon relative equals to 1, and of course mu relative equals to 1. U should be 3 times 10 to the power 8 meters per second. So now let's solve another example. We are asked to calculate the wavelength for a plane wave that propagates in vacuum, and we have multiple frequencies. Actually, your book has the question in your book consists of 4 parts: A, B, C, and D. I added 2 parts to make it more interesting. So one reason why we want to operate at higher frequencies is that the antenna size is always proportional to the wavelength. So in general, the antenna length is somehow close to wavelength divided by 2. So let's find the wavelength for a 60 Hertz transmission line for a 60 Hertz frequency. We assume that it operates in free space. So A is then we can use this formula to find the wavelength. Which is 5 times 10 to the power 6 meters, or if we want to express this in terms of kilometers, we get 5 times 10 to the power 3 kilometers. So imagine that we have an antenna that's half of that. So 2,500 kilometers. So that's one reason why we don't transmit power using wirelessly. So now let's go to the second part, which is f equals to 2 megahertz. This is very close to the frequencies of the AM radio. The wavelength is C again divided by F, which is 150 meter. The third one is F equals to 120 megahertz, which is usually the frequencies around the frequencies of the FM radio. So the wavelength is 2.5 meters. If we go to 2.4 gigahertz, which is the bandwidth or the frequency of the microwave oven, or at the same time it's the frequency of the Wi-Fi. It's one of the frequencies of the Wi-Fi. So the wavelength is 12.5 centimeters. If we move up in frequency, when f equals to 12 gigahertz. So this one is very close to satellite communication. Lambda equals to 2.5 centimeters. If we go to when f equals to 28 gigahertz, this is one of the bands for the next generation for the for 5G. So the wavelength is almost 1 centimeters. So we see here, if we go up in frequency, the wavelength shrinks, and in electromagnetic, everything is actually the dimension that we mostly care about is the wavelength. So things that are short in absolute distance might be very long in electrical length or electrical distance, depending on the frequency of operation or the frequency of pop